Two worlds were born as nearly identical twins. They formed from the same swirling cloud of gas and dust, orbiting the same star, crafted from the same fundamental ingredients. One is our home, a vibrant blue marble teeming with life. The other is a scorching, acidic inferno where lead flows like water and the sky crushes down with unimaginable force. This is the profound mystery of Venus and Earth. By the end of this exploration, you will understand the precise chain of events that doomed one world while sparing the other, revealing just how fragile a habitable planet truly is. We will investigate a lost ocean, a runaway atmospheric disaster, and a geological engine that failed to start. How does a planet so similar to our own become a permanent warning written in the clouds? The story of these twin planets forces us to ask a deeper question about our own place in the cosmos. What does it mean that our world survived? Their shared origin is the very reason their split is so startling. For all their dramatic differences today, Venus and Earth began as planetary siblings, forged under the same cosmic conditions. They are almost identical in size and mass, which means their gravity and fundamental structure were a near-perfect match from the start. They condensed from the same swirling disk of material around our young sun, and computer models suggest they formed at a very similar distance from it, well within what astronomers call the habitable zone, the region where liquid water can exist on a planet's surface. They were built from the same ingredients, rocky metals and silicates, with a similar internal blueprint of a metallic core, a rocky mantle, and a thin crust. In those first few 100 million years, the scene on both worlds would have been nearly indistinguishable and utterly terrifying. The energy of countless asteroid impacts and the decay of radioactive elements inside kept their surfaces entirely molten, a global ocean of magma. From these fiery cauldrons, both planets degassed or released their primordial atmospheres. The same volatile compounds bubbled up through the magma and filled their skies, a thick, stifling blanket of carbon dioxide and water vapor, with traces of nitrogen and sulfur. This is a critical point. Their starting atmospheres were essentially the same recipe. Then, as the bombardment slowed and the surfaces began to cool and solidify, something remarkable likely happened on both worlds. That thick water vapor in the atmosphere would have begun to condense, and for perhaps hundreds of millions of years, warm, torrential rains may have fallen on the newborn rock of both Venus and Earth, slowly filling vast basins. Many planetary scientists believe it is entirely possible, even probable, that young Venus sported a shallow, global ocean, not so different from the one that covered the early Earth. This is the baseline, the shared starting line for our twin planets. Two wet, rocky worlds of similar size with similar atmospheres, orbiting in the same favorable neighborhood of the same star. One would nurture that potential into a living biosphere. The other would see it all evaporate into a cosmic nightmare. The question that haunts us is not how they were different, but what subtle trigger, what single domino, fell first to set them on entirely separate paths. The world we see today is a monument to planetary catastrophe. Venus is a place where the very idea of a surface is a misnomer, for it is less a landscape and more a crushing, superheated fluid of gas. The numbers alone paint a terrifying picture. The average surface temperature is a sustained 870 degrees Fahrenheit, hot enough to not just melt lead, but to keep it in a shimmering, liquid state. The pressure bearing down from above is equivalent to the weight found nearly 3,000 feet beneath Earth's ocean, a staggering 90 times what we experience at sea level. It is an environment where a human probe would be simultaneously incinerated, crushed, and dissolved within minutes. This immense pressure comes from an atmosphere almost unimaginably thick and toxic. Over 96% of it is carbon dioxide, a greenhouse gas that, in such staggering concentration, acts like a smothering thermal blanket with no off switch. Trapped beneath this blanket, the sun's heat has nowhere to go, creating the extreme temperatures that define the planet. And high above this oven, completing the portrait, are those beautiful, deceptively reflective clouds. They are not made of water, but of sulfuric acid, a global shroud that rains acid droplets that evaporate long before they could ever reach the inferno below. This is the crucial point to remember. This hellscape is not what Venus was born as. It is the end result, the final, stable state of a process that ran away with itself completely. The planet we observe is a fossilized climate disaster, a warning of what happens when a world's balancing systems fail. To understand how it got here, we must rewind the clock and look for the first subtle crack in its planetary machinery. Our world possesses a hidden, dynamic rhythm that Venus tragically lost. Earth is not a static paradise, but a planet in constant, delicate negotiation with itself. While Venus succumbed to a runaway disaster, Earth developed a series of brilliant, self-regulating systems that act like a planetary immune system, constantly correcting for imbalance. The most important of these is a slow, powerful geological process we call the carbon-silicate cycle. Think of it as Earth's built-in thermostat, a feedback loop that operates over hundreds of thousands of years. Here is how it works. Carbon dioxide from the atmosphere dissolves in rainwater, forming a weak acid. This acidic rain falls on mountains and continents, slowly wearing down the rock in a process called chemical weathering. The dissolved carbon minerals are then carried by rivers to the oceans. There, tiny marine organisms use them to build their shells and skeletons. When these creatures pass on, their remains sink to the seafloor, locking that carbon away in layers of sedimentary rock like limestone. This process continuously pulls carbon dioxide out of our atmosphere. Now, if the planet gets too cold, this weathering slows down. Meanwhile, volcanoes keep belching new carbon dioxide from deep within the Earth. With less being pulled out, the greenhouse gas slowly builds back up, warming the planet again. If it gets too warm, weathering accelerates, pulling more carbon dioxide down faster, cooling things off. This incredible cycle has maintained Earth's climate within a habitable range for billions of years, despite the sun growing steadily brighter. Venus, for reasons we will soon discover, lost its ability to perform this critical dance. But Earth's advantages did not stop there. Our planet also has a strong global magnetic field, generated by the churning of molten iron in its core. This magnetic bubble deflects the relentless stream of charged particles from the sun, known as the solar wind. Without this shield, that wind would have slowly, relentlessly stripped away our atmosphere molecule by molecule, leaving us exposed and barren. And then there is our large, singular moon. Its gravitational pull acts as a steadying hand on Earth's rotation, preventing wild, chaotic swings in our axial tilt. This stability gives us predictable seasons and a relatively steady climate over eons. Venus, by contrast, tumbles slowly on its side with no such lunar anchor. Each of these factors alone is remarkable, but together they formed a protective, stabilizing triad that allowed life to gain a foothold and our oceans to endure. The haunting question then becomes, why did Earth develop this elegant suite of safeguards while its twin, starting from the same point, did not? The answer lies in a single, pivotal difference that set everything in motion. The fate of Venus was sealed by a simple, terrifying physical law with no off switch. This is the runaway greenhouse effect, a chain reaction that once begun cannot be stopped. To understand it, picture a planet like early Venus, with liquid water on its surface and a modest atmosphere. Sunlight warms the ground, and the ground radiates heat back out toward space as infrared energy. Greenhouse gases like carbon dioxide and water vapor in the atmosphere absorb some of that outgoing heat, trapping it and keeping the planet comfortably warm. This in itself is a good thing. Earth benefits from this same gentle greenhouse effect. The disaster begins with just a little extra push. Perhaps the young sun was slightly brighter, or volcanic activity released a large pulse of carbon dioxide. That small nudge raises the planet's temperature by just a degree or two. Here is where the feedback loop ignites. That tiny increase causes more water to evaporate from the oceans and land. Water vapor is itself an incredibly powerful greenhouse gas. So now, with more water vapor in the air, even more heat gets trapped. The planet warms another degree. This causes even more evaporation, putting still more water vapor into the atmosphere, which traps yet more heat. The cycle feeds itself, accelerating wildly. Temperatures climb higher and higher, driving the oceans to boil. All that water, once a liquid lifeblood, becomes a gaseous fuel for the fire, supercharging the greenhouse effect beyond any natural limit. This is the threshold, the point of no return. Once the oceans begin to vaporize entirely, the process becomes irreversible. The planet hurtles toward a new, permanent equilibrium, a scorching world where all water is locked in the atmosphere or lost to space, and the surface bakes under a thick carbon dioxide sky. This is not a slow change. It is a climatic avalanche, and for Venus, this avalanche did not just alter the climate, it dismantled the very possibility of a future like Earth's. But what was the first push, the initial nudge that sent Venus tumbling down this irreversible path? The planet's closer proximity to the Sun is the most obvious suspect. Venus orbits roughly 30 million miles nearer to the Sun than Earth does. While that may not sound like a lot on the cosmic scale, it means Venus receives almost twice the solar radiation that our planet does. From the very beginning, its climate operated on a hotter, more precarious setting. That extra energy meant its early oceans were warmer, its atmosphere more energetic. In this state, the balance was far more delicate. A relatively small perturbation, something Earth might have shrugged off, could have been enough to tip the scales. Think of it like two identical cups, one placed closer to a faucet. The closer cup fills faster and is more likely to overflow with just a little extra splash. Venus was that closer cup, constantly receiving more heat, making the transition from a stable climate to a runaway greenhouse a much easier threshold to cross. Yet distance alone may not tell the whole story. Another powerful catalyst could have been a period of catastrophic volcanism. In its youth, Venus may have experienced a global resurfacing event, a planetary-scale eruption that flooded its plains with lava for millions of years. Such an event would have vomited colossal amounts of carbon dioxide and other gases directly into the atmosphere. On Earth, our carbon cycle would have eventually drawn much of that gas back down into the rocks. But if Venus's volcanic pulse was too intense and too sudden, it could have overloaded the atmosphere, providing that critical shove into the feedback loop. The extra heat from the added carbon dioxide could have begun evaporating the oceans, and from there, the cycle would have taken on a life of its own. There is a third, more subtle factor that may have sealed the planet's fate: the loss of its magnetic shield. Planetary scientists believe Venus may have once had a magnetic field, generated by the churning of a molten metal core. But without a large moon to stir its interior through gravitational tides, or due to differences in its internal composition, that churning may have slowed and stopped early on. The protective magnetic bubble would have collapsed, leaving the atmosphere fully exposed to the solar wind. This relentless stream of charged particles from the Sun could have begun stripping away the lighter molecules, particularly hydrogen from water vapor. Over eons, this process, known as atmospheric erosion, would have slowly desiccated the planet, removing the very substance that could have eventually rained back down to cool the surface. It is a haunting possibility that these triggers may have worked in concert. A stronger solar push, a massive volcanic shove, and the slow stripping of its protective shield together could have overwhelmed a world that was already living on the climatic edge. The tragedy of Venus is that it likely never stood a chance to develop the self-correcting systems that saved its twin. The disappearance of its oceans is the silent crime seen in this planetary mystery. If Venus once cradled vast, warm seas as scientists suspect, then every single drop is now gone, vanished without a trace from the scorched surface. To understand how, we must look high above the clouds to where sunlight itself performs a slow, relentless act of destruction. This process is called photodissociation, and it is the primary suspect in the case of the missing water. High in Venus's upper atmosphere, even today, any remaining traces of water vapor are exposed to the full fury of solar ultraviolet radiation. These powerful rays slam into the water molecules, H2O, and violently break them apart. The oxygen and hydrogen atoms are sent flying. The heavier oxygen often gets captured by other compounds, but the lightweight hydrogen, now free and unbound, faces a critical moment. On a world with a strong magnetic field like Earth's, that hydrogen might be corralled and protected, but Venus, lacking that global shield, offers no such protection. The relentless solar wind, that stream of charged particles from the sun, sweeps past and easily picks up these liberated hydrogen atoms, carrying them away into the void of interplanetary space forever. It is an irreversible loss. Each broken water molecule represents a tiny, permanent subtraction from the planet's total inventory. Over hundreds of millions of years, this slow drip of atomic escape could have drained an entire global ocean. Now contrast this with Earth's story. Our planet holds onto its water for two key reasons. First, our greater distance from the sun means we receive less intense ultraviolet radiation, so the process of photodissociation happens at a much slower, more manageable rate. Second, and more crucially, our planet's strong magnetic field acts as an immense protective umbrella. It deflects the vast majority of the solar wind, preventing it from reaching deep into our atmosphere and stealing our hydrogen. The water molecules that are broken apart high above Earth often have their components recirculated or temporarily held, rather than instantly lost. This fundamental difference in planetary defense explains why Earth's blue marble remains wet, while Venus became a parched and endless desert. The water did not just boil away, it was systematically taken apart and stolen by the sun, molecule by molecule, in a theft that lasted eons. This bizarre spin is perhaps the strangest clue in the entire mystery. While Earth pirouettes once every 24 hours, Venus turns with an almost imperceptible slowness. A single day on Venus, the time it takes to complete one full rotation, lasts 243 Earth days. To make this cosmic oddity even more profound, its year, the time it takes to orbit the Sun, is only 225 Earth days. On Venus, a day is literally longer than a year. And as if that were not strange enough, it spins in the opposite direction of almost every other planet in our solar system. From a hypothetical surface, the Sun would rise in the west and set in the east. This profoundly abnormal rotation was not a minor quirk. It was a planetary scale handicap with devastating climatic consequences. Think about what a rapid rotation does for Earth. Our 24-hour cycle creates a powerful, moderating rhythm. The Sun's intense heat is never focused on one side of the globe for too long. As our planet turns, the heated air and oceans are constantly being carried away from the scorching equator toward the cooler poles, and nightfall regularly relieves the land of the Sun's direct glare. This creates global wind patterns and ocean currents that act like a giant stirring spoon, mixing the atmosphere and efficiently distributing heat around the entire planet. This prevents any one region from baking indefinitely or freezing in permanent shadow. Venus, with its agonizingly slow spin, lost this vital stirring mechanism. Imagine one hemisphere locked in continuous, blistering daylight for over 4 Earth months. The ground and atmosphere on that sunlit side would have time to heat to staggering extremes. Meanwhile, the opposite hemisphere would languish in a cold, months-long night. Without a fast rotation to drive strong global winds, the atmosphere would struggle to move this intense heat from the day side to the night side. The result would be a planet of radical, sustained temperature extremes, not a globally uniform oven. This inefficient heat distribution likely created stagnant, sluggish weather systems. More critically, it may have crippled the very process that could have saved Venus, the carbon cycle. On Earth, rainfall and weather driven by our rapid rotation are key agents of chemical weathering, the process that pulls carbon dioxide from the air. On a world with weak atmospheric circulation and little temperature contrast to drive storms, that weathering may have ground to a halt very early on. With no efficient way to pull down greenhouse gases, and with the sun beating down on one side for what felt like an eternity, the atmosphere would have grown thicker and hotter in a vicious, localized cycle. The slow rotation essentially broke the planet's thermostat before it could even be installed. So we are left with a haunting chain of cause and effect. A weak or absent magnetic field may have allowed the solar wind to begin stripping the atmosphere and water. The closer proximity to the sun provided more energy to fuel the disaster. And the snail-like rotation ensured that when the greenhouse effect began to run away, there was no planetary mechanism left to circulate, moderate, or mitigate the heat. It was a perfect storm of planetary failures, each one making the next catastrophe more inevitable. The final, and perhaps most decisive, difference lies not in the sky, but deep within the rock itself. While Earth's surface is a dynamic, ever-shifting puzzle of moving continents, Venus presents a single, unbroken shell of crust. This is the contrast between a living, breathing geological engine and a world frozen in a stagnant lid. On our planet, the brittle outer crust is fractured into a dozen or so massive plates that float on the hot, ductile mantle below. These plates are in constant, slow motion, driven by the immense heat rising from Earth's core. Where they pull apart, new crust is born from upwelling magma. Where they collide, one plate can be forced down beneath another in a process called subduction, diving back into the fiery mantle to be recycled. This grand cycle, plate tectonics, is far more than just a mechanism for making mountains and earthquakes. It is Earth's ultimate climate regulator, its long-term carbon thermostat. Here is how it works. Over millennia, atmospheric carbon dioxide dissolves in rainwater and weathers surface rocks. The dissolved minerals are washed into the oceans where they settle as sediment on the seafloor. This is where plate tectonics performs its crucial act. When an oceanic plate subducts, it drags those carbon-rich sediments and seafloor rocks down into the mantle. The carbon is effectively removed from the surface environment and stored deep underground for millions of years. Later, some of that carbon can be released back into the atmosphere through volcanic eruptions, completing a cycle that spans eons. This process provides a slow, steady pressure release valve for atmospheric carbon, preventing it from building up to catastrophic levels. Venus tells a completely different geological story. Observations from orbiting radar satellites reveal a surface covered in vast volcanic plains, enormous shield volcanoes, and strange, deformed regions called coronae. But crucially, there are no long, linear mountain chains, no clear evidence of continental drift, and no globe-encircling network of plate boundaries. Instead, most planetary scientists believe Venus operates in what is called a stagnant-lid mode. Its entire crust forms one continuous, unbroken plate that essentially caps the planet like a solid lid on a simmering pot. Heat from the interior still needs to escape, so it does so in fits and starts. The mantle below grows hotter and hotter until it finally manages to melt through the thick lid in a massive, regional upwelling of lava, flooding vast areas before the lid reseals itself. This episodic, catastrophic volcanism may explain Venus's relatively young, uncratered surface, but it lacks the continuous, global conveyor belt of subduction. Without subduction, there is no efficient pathway to pull carbon from the atmosphere and lock it away in the mantle. Instead, volcanic eruptions on Venus would have done nothing but pump more and more carbon dioxide into the air, where it would accumulate with no long-term removal system. Imagine two houses with wood stoves. One has a chimney that vents the smoke outside. The other is sealed shut, with the owner occasionally opening a window to toss in more wood before slamming it closed again. The first house manages the smoke, the second one fills with it until it becomes unbearable. Earth has the chimney, Venus, with its stagnant lid, does not. This single geological difference meant that any carbon dioxide released into Venus's atmosphere, whether from early volcanism or later from the boiling oceans, was effectively trapped forever. The planet's thermostat was broken before it was ever built, locking in the heat that would define its future. This invisible shield is the silent guardian of our blue world. Earth possesses a powerful, planet-wide magnetic field, a force field generated by the churning of molten iron in its outer core. Think of it as a colossal, dynamic bar magnet embedded deep within the planet, its lines of force arcing out into space for tens of thousands of miles. This magnetic bubble, called the Magnetosphere, is our first and most vital line of defense against the constant stream of charged particles blasted from the sun, known as the solar wind. Without this shield, that wind would act like a cosmic sandblaster, slowly but relentlessly stripping our atmosphere away molecule by molecule, particularly the lightest elements. Our air and our water would be vulnerable to a slow, irreversible theft by space itself. This is not a hypothetical danger. We see it happening today on Mars, a smaller world whose internal dynamo faded long ago, leaving it with only a thin, wispy atmosphere and a dry, barren surface. Earth's magnetic field deflects the vast majority of the solar wind, pushing it around our planet and funneling only a small fraction toward the poles, where it creates the beautiful, harmless auroras. It is a perfect dynamic defense system powered by the planet's own internal heat and rapid rotation. That last part, the rapid rotation, is the crucial piece Venus tragically lacked. Planetary scientists believe a global magnetic field is generated by what is called a dynamo effect. For this to work, you need a fluid, electrically conducting core like molten iron, and you need that fluid to be in vigorous, turbulent motion. Earth's relatively fast 24-hour spin provides a critical stirring force, helping to drive the complex convection currents in its outer core that generate our protective magnetic bubble. Venus, with its agonizingly slow 243-day rotation, simply does not have that same driving energy. Its core may have once been molten and active, but without the vigorous stirring from a fast spin, the internal dynamo likely sputtered and died early in the planet's history. The result was a catastrophic vulnerability. Venus was left without a global magnetic shield. Its atmosphere from the very beginning was fully exposed to the full force of the solar wind. This meant that as the runaway greenhouse effect began and water vapor filled the upper atmosphere, the process of photodissociation had a devastating partner. When solar ultraviolet radiation broke apart the water molecules, the liberated hydrogen atoms were not protected or recirculated. Instead, the unimpeded solar wind could sweep them up and carry them off into space forever. This 1-2 punch of dissociation and stripping ensured that any water lost from the surface was a permanent loss. The planet could not simply cool down later and have the rains return because the fundamental ingredient, the hydrogen, was gone. So while Earth's magnetic field safeguarded the volatile compounds essential for life, Venus stood naked before the sun, watching its future literally evaporate into the void. Yet another cosmic clock was ticking against Venus, one that began with the Sun itself. Our star was not born with the brightness we know today. In its youth, over 4 billion years ago, the Sun was significantly fainter, emitting only about 70% of the light and heat it radiates now. Astronomers call this the faint young sun paradox because it presents a fascinating puzzle. If the early Sun was so dim, why wasn't the early Earth a frozen ball of ice? The answer lies in Earth's own clever geology, that carbon cycle thermostat we discussed, which maintained warmth through a thicker blanket of greenhouse gases. But for Venus, this faint young sun changes the entire timeline of its tragedy. Think of the Sun's gradual brightening as a slowly turning dial on a cosmic heater. For hundreds of millions of years, that weaker sunlight may have been the only thing keeping Venus's climate in check. Under that cooler, gentler sun, the planet's closer orbit might not have been the death sentence it became. A temperate Venus with possible liquid water oceans could have been a stable reality for a very long time. It was a borrowed grace period, but the dial kept turning imperceptibly year by year, millennium by millennium. As the Sun grew steadily brighter through nuclear fusion in its core, the extra energy flooding into the inner solar system became more and more intense. Venus, by virtue of being the closest rocky planet, would have felt this increase first and most severely. There is a moving boundary in space called the inner edge of the habitable zone, the point where a planet becomes too hot for liquid water to survive. As the Sun brightened, that boundary slowly crept outward, and Venus, parked in its orbit, was the first world in its path. At some critical moment, the increasing solar radiation provided that final, unavoidable push. The extra heat likely accelerated evaporation from any remaining seas, pumping more water vapor into the air. That potent greenhouse gas trapped more heat, which evaporated more water, and the feedback loop we described earlier finally ignited in earnest. The faint young sun had given Venus a long, perhaps habitable childhood, but its inevitable maturation into the brighter star we know today sealed the planet's fate. It crossed the threshold first, becoming a permanent warning of what happens when a world's balancing systems cannot keep pace with a changing star. The geological scars on Venus tell a story of planetary violence on an unimaginable scale. Orbiting radar missions, most famously Magellan in the 1990s, mapped the surface in stunning detail, revealing a world of vast volcanic plains, towering shield volcanoes, and strange, wrinkle-like ridges. But one feature was conspicuously, hauntingly absent. There were almost no impact craters. For a planet in the inner solar system, bombarded for billions of years, this is profoundly strange. The surface of Venus appears remarkably young, with an estimated age of only 500 to 700 million years. The inescapable conclusion is that the entire planet was repaved, quite literally, in a single catastrophic event. Planetary scientists call this a global resurfacing. The leading theory is that heat, trapped for eons beneath the planet's stagnant lid of crust, built to a critical breaking point. The entire lid then fractured and foundered, sinking into the mantle in a geological cataclysm. In its place, unimaginable floods of lava erupted from thousands of fissures, covering nearly every square mile of the planet in fresh, new basalt in a period that may have lasted only a few million years. This was not like the steady, piecemeal volcanism we see on Earth. This was the planet vomiting its entire interior onto its skin in one feverish, planet-wide convulsion. The climatic consequences of such an event would have been apocalyptic. Think of the carbon dioxide released by a single large volcano on Earth, and then multiply that by 10,000, by 100,000. A global resurfacing would have injected an almost incomprehensible volume of greenhouse gases directly into Venus's atmosphere in a geological instant. For a world already teetering on the edge, this would have been the final, decisive blow. Any last vestiges of a temperate climate, any remaining pockets of liquid water, would have been utterly erased beneath this sudden, suffocating blanket of gas. The planet's temperature would have skyrocketed, permanently locking in the runaway greenhouse state we observe today. Contrast this with Earth's geological heartbeat. Our planet's tectonic plates move at the speed a fingernail grows, a slow, steady conveyor belt that constantly recycles crust and regulates atmospheric gases over millions of years. It is a system of gradual release and renewal. Venus, with its stagnant lid, had no such pressure valve. Its heat built up until the entire system exploded, resetting its surface and its fate in one terrible, definitive act. This event raises a chilling possibility. Perhaps Venus was not always the hellscape it is now. Perhaps for billions of years before this resurfacing, it clung to a fragile, more temperate existence. The global ocean we suspect may have persisted, its skies perhaps even clement. Then the planet's own internal furnace, unable to vent its heat in a steady trickle, finally burst. In a single geological moment, Venus did not just change its face. It committed a form of planetary suicide, ensuring its twin paths with Earth would never cross again. The sequence of disasters may be the most crucial clue of all. It is not just what happened to Venus, but the precise order in which it happened that doomed the world. Imagine two planets facing the same series of challenges, but receiving them in a different chronological order. One planet might weather the storm while the other is overwhelmed. This is the subtle yet profound difference between a near miss and a permanent catastrophe. For Venus, the deck was stacked from the very beginning in the worst possible sequence. Its closer orbit to the Sun meant it received that critical first push into instability earlier in its history, likely while it was still geologically young and its systems were not yet robust. The extra solar energy may have begun evaporating its primordial oceans and pumping water vapor into the atmosphere, triggering the early stages of a runaway greenhouse effect. This was a negative feedback loop, a self-reinforcing cycle of heating that started spinning out of control. Crucially, this climate disaster began to unfold before the planet could establish the long-term, stabilizing systems that might have saved it. On Earth, the sequence appears to have been almost perfectly reversed. Our slightly more distant orbit bought us precious time. The gentler early sun allowed Earth's surface to cool and solidify more stably. During this critical grace period, something remarkable happened. The geological engine of plate tectonics likely began to stir. Liquid water pooled and persisted, enabling the chemical weathering that starts the carbon cycle. These are positive feedbacks for habitability. Systems that, once started, worked to maintain a stable, temperate climate. They became established and locked in before the sun's increasing brightness or other major stresses could push the climate over the edge. By the time Earth faced its own serious challenges, it had a fully functional planetary immune system already in place, a suite of thermostats and buffers that could absorb the shock and correct the imbalance. Venus had no such luck. The heating began so early that it may have prevented the very conditions needed for plate tectonics to start. A hotter, more plastic crust might not have fractured into moving plates, but instead remained a stagnant, unbroken lid. Without plate tectonics, there was no carbon cycle to pull greenhouse gases back into the rock. Without that cycle, the heating accelerated, boiling away the oceans. And without liquid water, the crust became even more rigid, forever sealing the planet's fate in a tragic catch-22. The timing was everything. Venus experienced its crisis during its planetary infancy, when it was most vulnerable. Earth enjoyed a stable childhood, allowing it to build the resilience needed to survive its own adulthood challenges. In this light, habitability is not just about having the right ingredients, but about having them assemble themselves in the right order against a clock that is constantly ticking. The standard model of Venus's fate is compelling, but the cosmos is rarely that simple. Some scientists wonder if a single, violent event could have set the entire tragic sequence in motion. Imagine a protoplanet, perhaps as large as Mars, on a collision course with a young, spinning Venus. Such a titanic impact, occurring in the chaotic early solar system, could have delivered a glancing blow with enough force to dramatically slow the planet's rotation, or even flip it entirely, leaving it spinning backwards and at its current snail's pace. This is a compelling idea because it provides a clean, catastrophic explanation for Venus's most bizarre feature, its retrograde spin. If true, it means the planet's climatic doom was not an inevitable result of its orbit, but a random stroke of cosmic bad luck, a brutal hit that broke its natural day-night rhythm before it could ever establish a stable climate. The impact itself would have been apocalyptic, possibly vaporizing any early oceans and filling the sky with molten rock and searing vapor, creating the perfect initial conditions for a greenhouse atmosphere to take hold and never let go. Another speculative thread involves the Sun's gravitational pull. Given its closer proximity, some models suggest that early Venus may have experienced a form of tidal locking, where one face permanently pointed toward the Sun, much like our Moon always shows one face to Earth. In this scenario, the planet would have had a permanent day side, a scorching desert, and a permanent night side, a frozen wasteland. Such an extreme temperature difference would have created unimaginably fierce winds, but it also would have made a global, temperate climate an impossibility from the start. Any water would have been trapped as ice on the dark side, while the sunlit hemisphere baked. Over time, as the planet's orbit and spin evolved, it could have unlocked from this state, but the damage to its atmospheric and water inventory may have already been done during that first, locked epoch. This theory suggests Venus was born into a climate prison, its fate sealed by celestial mechanics before it even had a chance. The most profound and most controversial speculation asks a breathtaking question. Could Venus have ever been alive? A small number of researchers have pondered whether, during its possible ocean-bearing youth, simple microbial life might have briefly gained a foothold in its seas or clouds. If it did, that life would have faced a desperate, losing battle against the rising heat. In a struggle for survival, microbial metabolisms can produce gases as byproducts. On a global scale, a dying biosphere might have significantly altered the atmospheric chemistry, perhaps even accelerating the greenhouse effect in its final throes. This is not a claim that Venus once had forests or oceans teeming with creatures, but rather a thought experiment about the faintest possibility of a microbial spark that flickered and went out, its chemical signature long since erased by billions of years of volcanic repaving and atmospheric chaos. It remains a fringe idea because the evidence is so utterly lost to time, but it underscores a deeper point. We study Venus not just as a cautionary tale, but as a reminder that the line between a living world and a dead one might be terrifyingly thin, and that biology itself can become an unwitting architect of its own extinction if the planetary systems fail. These alternative paths are not yet the mainstream story, but they are vital to the scientific process. They represent the edges of our understanding, where researchers ask the what-if questions that challenge comfortable narratives. Whether by random impact, tidal forces, or a fleeting whisper of biology, these speculations all point to the same haunting conclusion. Venus's journey to hell was not a single mistake, but a cascade of misfortunes, where geology, astronomy, and perhaps even the faintest brush with biology conspired to close every door that remained open for Earth. As we look at our own world with its balanced climate and blue skies, these theories force us to appreciate not just the systems that protect us, but the sheer, fragile luck that allowed them to form in the first place. The story of these twin worlds forces us to rewrite the cosmic rulebook for finding life elsewhere. For decades, the search for habitable planets focused on a simple, elegant idea known as the Goldilocks zone, or more formally, the circumstellar habitable zone. This is the orbital band around a star where temperatures are just right, not too hot and not too cold for liquid water to exist on a planet's surface. It was a beautiful, distance-based concept calculated purely on the physics of starlight and planetary heat. Venus, however, is a permanent monument to the profound flaw in that simple model. It orbits within the Sun's traditional habitable zone, yet its surface is a scorching, airless hellscape. Its existence screams a fundamental truth that distance from a star is only the first, and perhaps the least important, question we need to ask. The Venus-Earth comparison has shattered the old static model and replaced it with a dynamic, multidimensional understanding of planetary habitability. We now see that a planet's history, its geology, its rotation, and its magnetic shield are not secondary details. They are the primary architects of its climate. The habitable zone is not a fixed ring in space. It is a delicate state of being that a planet must actively maintain through its own internal machinery. A world can be in the perfect spot and still be a sterile oven if it lacks the right planetary systems, just as a world slightly farther out might thrive if it possesses a robust geological thermostat and a protective magnetic bubble. This reframes our entire search for life in the cosmos. Astronomers hunting for exoplanets, those distant worlds orbiting other stars, now look with a more discerning eye. Finding an Earth-sized planet in the habitable zone of a Sun-like star is an exciting discovery, but it is no longer the finish line. It is merely the starting gate. The real investigation begins with questions Venus taught us to ask. Does this world likely have plate tectonics? What is its rotation period? Could it maintain a global magnetic field? Does its star bombard it with flares that could strip away an atmosphere? The answers to these questions, gleaned from subtle clues in starlight and shadow, will tell us if a planet is truly a living world like Earth or a fossilized climate disaster like Venus, forever trapped in the habitable zone but eternally uninhabitable. Our own solar system, with its stark twin planets, has given us the ultimate comparative laboratory, a before and after picture of planetary destiny. It teaches us that life is not a default setting for a rocky world in the right place. It is the rare, exquisite product of 1,000 delicate systems aligning in the right sequence and persisting across billions of years. Every new exoplanet we find is now measured against the twin fates of Venus and Earth, a constant reminder that in the grand cosmic story, a world's character is just as vital as its address. Venus stands in our sky as a permanent monument to a climate pushed past the point of no return. While our planet can never become an exact copy of that scorching world, the ghost of Venus whispers a sobering lesson in the language of physics. The runaway greenhouse effect that transformed it is governed by the same fundamental principles that drive global warming here on Earth. Both involve the trapping of heat by gases in the atmosphere, primarily carbon dioxide. The difference is one of degree, not kind. On Venus, the process ran to its ultimate, horrifying conclusion, boiling away oceans and baking the rock. On Earth, we are witnessing the early, human-accelerated stages of that same physical process, a forcing of the planetary thermostat through the immense release of buried carbon from fossil fuels. The core mechanism is identical, and it grants Venus a terrible authority as a climate change analog, a nearby example of what happens when greenhouse gas accumulation is left unchecked by any balancing force. This parallel offers a crucial insight into the danger of feedback loops. Venus succumbed to powerful positive feedbacks where a little warming caused changes that led to even more warming. We see similar, though less extreme, amplifiers activating on Earth today. As polar ice melts, it exposes darker ocean or land that absorbs more sunlight, accelerating further melting. Warmer temperatures increase the frequency and intensity of wildfires, which release more carbon stored in forests. Thawing permafrost can release ancient stores of methane, a greenhouse gas dozens of times more potent than carbon dioxide. These are not hypotheticals, they are observed processes. Venus shows us where such cycles can lead if they become dominant, flipping a planet from one stable state to another, far less hospitable one. The transition may not be a slow, gentle slope, but a sudden, irreversible cliff. It is vital to state clearly that Earth's greater distance from the Sun provides a fundamental safety buffer Venus never had. Our orbit places us in a position where a full Venus-style runaway, with oceans boiling into the sky, is not physically possible with the carbon we have available to burn. This is an important scientific distinction. The ultimate fate of Venus is not our destiny, yet this fact should not breed complacency, but rather clarify the real danger. We will not create a second Venus, but we can absolutely and are actively pushing Earth toward its own unique tipping points, toward a new equilibrium that is profoundly disruptive to human civilization and the biosphere we depend on. The planet will survive, but our societies, agriculture, and coastal cities may not emerge intact from a radically altered climate state. So what does Venus, this fossilized climate disaster next door, truly warn us about? It warns that planetary systems have thresholds. It demonstrates that once certain processes gain momentum, they can become self-sustaining and exceedingly difficult to halt. It proves that a world can transition from a state of potential abundance to a state of permanent sterility. For humanity, the lesson is not about replicating Venus, but about understanding the profound responsibility that comes with tinkering with a planet's atmospheric chemistry on a global scale. We are conducting a massive, unplanned experiment with the only life support system we have. Venus shows us the ultimate consequence of a greenhouse effect left to run wild, a reminder written in acid clouds and scorched stone that some changes, once set in motion, echo for billions of years. After billions of years as a cautionary tale, Venus is finally getting a second look. A new fleet of robotic explorers, equipped with technology unimaginable to earlier generations, is being prepared to pierce the planet's thick clouds and uncover its deepest secrets. This is not merely a return, it is a full-scale scientific assault on the mystery, led by 3 groundbreaking missions from the world's leading space agencies. NASA is sending 2 complementary probes, DAVINCI and VERITAS, while the European Space Agency is contributing the EnVision orbiter. Together, they form a coordinated campaign to answer the very questions we have been asking, transforming speculation into hard data. Think of it as the ultimate cold case investigation, where the crime scene is an entire planet and the clues have been waiting for eons. DAVINCI, which stands for Deep Atmosphere Venus Investigation of Noble Gases, Chemistry and Imaging, is a daring descent probe. Its mission is to plunge directly into the Venusian atmosphere, a one-way journey of discovery. As it falls through the corrosive clouds for about 1 hour, its sophisticated instruments will act like a cosmic bloodhound, sniffing the air with precision never before possible. It will measure the exact ratios of noble gases like krypton and xenon, chemical fingerprints that hold secrets about how the planet formed and whether it ever had an ocean. Crucially, it will analyze trace amounts of water vapor and specific isotopes of hydrogen, searching for the chemical scars left by that ancient, catastrophic water loss. Was the water stripped away quickly by a violent event or slowly siphoned off over time? DAVINCI's chemistry lab, descending through the layers of hell, aims to find out. While DAVINCI takes the atmospheric sample, its sister mission, VERITAS, will be mapping the surface from orbit in stunning, radar-revealed detail. VERITAS stands for Venus Emissivity, Radio Science in SRR, Topography and Spectroscopy. This orbiter will create global, high-resolution topographic maps far superior to those from the Magellan mission, revealing the texture of the landscape down to the scale of a city block. But its most revolutionary tool will be a spectrometer designed to see through the atmosphere and identify the mineral composition of the surface rock. This is the key to Venus's geological past. By mapping where certain minerals, like those that form only in the presence of water, are found, VERITAS can search for the ghost of that lost ocean. It can also identify fresh lava flows, providing concrete evidence for whether Venus is volcanically active today, a question that speaks to the very heartbeat of the planet. The European Space Agency's EnVision orbiter will add another critical layer to this detective work. It will focus on the intimate relationship between the planet's atmosphere and its geology. Using a suite of instruments, EnVision will study how different surface features, like vast volcanoes or fractured tectonic zones, interact with the thick air above them. It will search for volcanic gases seeping from the ground and measure minute variations in gravity to probe the structure deep beneath the crust. EnVision's goal is to understand how the planet's interior, surface, and atmosphere evolved together over time, piecing together the sequence of events that led to the stagnant-lid world we see today. This trio of missions represents a new golden age of Venusian science. They move beyond simply describing the planet's present hellish state to actively reconstructing its biography. Each spacecraft is designed to test a specific part of the catastrophic story, from the chemistry of atmospheric escape to the geology of a world without plate tectonics. The data they return will not provide a single, simple answer, but will instead fill in the gaps in a complex planetary puzzle. We will learn not just what Venus is, but precisely how it became that way, step by irreversible step. For the first time, we are not just staring at the warning in the sky, we are sending investigators to read the fine print. The most profound unknown in this entire story is not how Venus died, but whether it ever truly lived. Confronting this question means staring into a deep abyss of time, where all direct evidence has been erased by billions of years of volcanic repaving and atmospheric chaos. Yet the possibility compels us because it reframes Venus from a cautionary tale into a potential tragedy, a world that might have glimpsed a biological dawn only to have it snuffed out forever. The arguments for an early habitable period are rooted in the fundamental similarities we have already explored. If Venus formed with the same water inventory as Earth, and if its orbit was stable within a cooler sun's habitable zone, then a global ocean could have persisted for perhaps 2 billion years. That is an immense stretch of time, longer than it took for life to emerge and fundamentally alter Earth's own atmosphere. A warm, shallow sea under a thick, protective carbon dioxide sky could have provided the same kind of nurturing chemical soup that fostered our planet's first microbes. The surface may have been a single, vast world ocean with few, if any, continents, a water world bathed in a perpetual orange twilight under those reflective clouds. In such an environment, the leap from chemistry to biology is not an absurd thought, but a hauntingly plausible one. The arguments against this hopeful scenario are equally powerful, and they center on timing and stability. Even under a fainter sun, Venus was always closer to the flame. Its grace period may have been shorter and more precarious than Earth's. The geological evidence, scant as it is, suggests the planet's surface is uniformly young, wiped clean by that global resurfacing event around 500 million years ago. If a clement epoch existed, it was erased in that planetary scale catastrophe, leaving no rocks from that era to study for fossilized clues. Furthermore, some climate models indicate that even with an ocean, Venus may have always been trending toward a greenhouse state, its atmosphere too thick, its rotation too slow to maintain a truly stable, global temperate climate for long geological periods. The window for life, if it ever opened, might have been a brief, flickering crack in time, not a long, steady dawn. This abstract debate was electrified by a controversial announcement in 2020. A team of astronomers reported detecting traces of a gas called phosphine in Venus's upper clouds. On Earth, phosphine is a stubborn biomarker, a gas that is notoriously difficult to produce in large quantities without biological activity, as it is quickly destroyed by natural chemical processes. The idea that it could exist in the temperate, high-altitude cloud decks of Venus, where temperatures and pressures are almost Earth-like, sparked immediate and intense speculation. Could hardy, airborne microorganisms be floating 50 kilometers above the scorching surface, eking out an existence in droplets of water and sulfuric acid? It was a breathtaking, almost science-fictional proposition. However, the scientific process is one of relentless scrutiny. Other research teams reanalyzed the data, and many could not confirm the phosphine signal, suggesting it might have been a misinterpretation of the spectral data from another sulfur compound common in Venus's atmosphere. The initial finding remains hotly debated, a tantalizing maybe that has not yet been confirmed, yet its true value lies not in proof but in provocation. It forced the entire field to look at Venus with fresh eyes and ask a question we had long considered settled. Could any niche, however extreme, harbor a form of chemistry we do not yet understand, or even biology itself? The sober consensus is that the surface of Venus today is utterly, unequivocally sterile. The combination of crushing pressure, scorching heat, and a lack of liquid water makes the existence of any life as we know it an impossibility. The ground is a geological purgatory, not a biological habitat, but the clouds are a different, strange environment altogether. While still profoundly acidic, the upper cloud layers have pressures and temperatures surprisingly similar to those on Earth's surface. Some scientists have rigorously modeled whether known extremophile microbes from our planet could theoretically survive there, suspended in aerosol droplets. The answer is a tentative, theoretical maybe, but the challenges are staggering. The droplets would eventually fall, descending into the lower, hotter layers and evaporating, forcing any hypothetical organism to somehow stay afloat in a vicious cycle of condensation and evaporation, all while bathed in sulfuric acid and bombarded by ultraviolet radiation. It is an incredibly hostile niche, but the universe has shown us that life can persist in the most unexpected places. The phosphine debate, even if ultimately disproven, has legitimized the study of Venus's atmosphere as a potential, if exceedingly unlikely, abode for life, pushing missions like DAVINCI to include instruments capable of detecting complex organic molecules. So where does this leave us with that profound unknown? The question of whether Venus ever harbored life remains one of the biggest open questions in planetary science, precisely because the answer is so devastatingly difficult to find. We are searching for a whisper that faded billions of years ago in a world that has melted its own history. The upcoming missions may find chemical hints, isotopic ratios that scream of a lost ocean, or mineral signatures on ancient highlands that only form in the presence of water. They might even detect unexplained chemical imbalances in the clouds, but they are unlikely to find a smoking gun, a fossilized microbe from a vanished sea. The truth may forever hover in the realm of compelling possibility, a ghost story written in the chemistry of the clouds and the scars on the rock. This enduring mystery transforms Venus from a mere object lesson in climatology into something far more poignant. It becomes a symbol of lost potential, a reminder that in the cosmos, a world with every apparent advantage can still fail, and that the spark of life, if it ever flickers, is a flame that must be fiercely protected, for the universe is full of winds that can blow it out for good. The most likely story of Venus begins with a deceptive calm, For perhaps its first billion years, the newborn planet was a world of promise, not punishment. It had coalesced from the same material as Earth, with a similar size and a similar inventory of water and carbon dioxide. Under the faint, young sun, its surface cooled enough for the steam in its thick atmosphere to condense. Torrential rains fell for millennia, slowly filling the low basins of its young crust. A shallow, global ocean likely came into being, a vast body of warm water under a perpetual cloudy orange sky. This was Venus's clement childhood, a period of potential that may have lasted for an astonishingly long time. In this early epoch, it might have even possessed a protective magnetic field and a faster rotation, though both were likely weaker than Earth's from the start. The stage was set, but the clock was already ticking against it. The first domino fell with the sun itself. As our star steadily brightened through nuclear fusion, Venus, by virtue of its closer orbit, felt the increasing heat first and most acutely. This was the initial, unavoidable push. The warmer temperatures began to evaporate more water from that global ocean. Water vapor is a far more potent greenhouse gas than carbon dioxide, so as more of it entered the atmosphere, it trapped more of the sun's heat. This caused the surface to warm further, which evaporated even more water. A positive feedback loop, slow at first but relentless, had been initiated. This was the beginning of the end for the oceans, a climatic spiral that would accelerate beyond any natural break. Around this same time, a second critical failure occurred deep within the planet. Venus's slower rotation meant its internal dynamo, the churning of molten iron that generates a global magnetic field, was starved of energy. The protective magnetic bubble sputtered and collapsed. With its shield gone, Venus's atmosphere was laid bare to the full force of the solar wind. Now, as the runaway greenhouse effect pumped water vapor high into the sky, solar ultraviolet radiation began breaking those molecules apart. The lightweight hydrogen atoms liberated by this photodissociation were easily swept away by the unimpeded solar wind, lost to space forever. The planet was not just boiling its ocean, it was systematically disassembling it and throwing the pieces into the void. This was a permanent loss. Even if the planet cooled later, the hydrogen, the essential ingredient for water, was gone. This dual atmospheric catastrophe, the runaway heating and the stripping of water, had a devastating knock-on effect on the planet's geology. Liquid water is not just for oceans, it is a vital geological lubricant. On Earth, water seeps into cracks in the crust, weakening rocks and helping to initiate the subduction process that drives plate tectonics. As Venus dried out, its surface became hotter and its crust grew stiffer and more rigid. The planet transitioned into what scientists call a stagnant-lid regime. The entire crust solidified into a single, unbroken plate, capping the planet like the lid on a pressure cooker. Without the conveyor belt of plate tectonics, there was no long-term mechanism to pull carbon dioxide out of the atmosphere and bury it in the mantle. Volcanic eruptions continued, but they only pumped more greenhouse gases into the air where they accumulated with no way out. The planet's thermostat was broken. Trapped beneath this stagnant lid, heat from the radioactive decay of elements in Venus's core began to build with no outlet. For hundreds of millions of years, pressure mounted. The surface, meanwhile, had become a scorching desert under a crushing carbon dioxide sky, a fossilized climate disaster. Then, around 500 to 700 million years ago, the lid could hold no more. In a planet-wide cataclysm, the entire global crust foundered and sank. Magma erupted from countless fissures, flooding virtually the entire surface in a geological instant. This global resurfacing event was the final act, repaving the planet in fresh lava and releasing one last, immense pulse of volcanic gases that permanently locked in the superheated atmosphere we observe today. It erased the last topographical hints of any ancient seas or continents, leaving behind the uniform volcanic plains we see now. This timeline is our current best fit model, a synthesis of orbital data, climate physics, and comparative planetology. It is not definitive truth, for the evidence is buried under eons of lava and acid clouds, but it paints a coherent and tragic portrait of a world that experienced a cascade of failures. Each misfortune made the next one more likely, until the original Earth-like planet was utterly transformed into its own opposite. The story of Venus is not one of a single mistake, but of a series of interconnected systems falling like dominoes, a reminder that a planet's habitability is a dynamic, fragile state, not a permanent condition. This fragile equilibrium we call home is the product of an improbable alignment. Our planet's continued habitability rests not on a single pillar, but on a carefully balanced array of planetary gifts, each one essential and each one absent on our twin. The first and most fundamental is our distance from the Sun. We orbit in that sweet spot where solar energy is strong enough to keep water liquid, but not so intense that it triggers an irreversible evaporation cycle. This optimal placement provided the stable foundation upon which everything else could be built. Yet distance alone would mean little without the dynamism that followed. Earth's rapid 24-hour rotation set our world in motion, literally and figuratively. That daily spin prevents the kind of extreme temperature contrasts that can destabilize a climate, and it drives the winds and ocean currents that circulate heat from the equator to the poles, mixing our atmosphere into a relatively uniform, breathable whole. More than that, our spin is the engine for a deeper magic. It stirs the molten iron in our outer core, generating the powerful global magnetic field that arcs around our planet. This invisible shield is our silent guardian, deflecting the relentless solar wind that would otherwise strip away our atmosphere molecule by molecule, as it likely did on Mars and contributed to the disaster on Venus. Our magnetic bubble protects the very air we breathe and the water vapor in our skies, holding onto the volatile ingredients of life. Beneath our feet, another monumental system hums along. The great geological engine of plate tectonics acts as Earth's long-term climate thermostat. Our fractured crust, constantly moving and recycling, provides a pathway for carbon dioxide to be pulled from the atmosphere, locked into rock, and later released through volcanoes in a cycle that spans millions of years. This process has maintained our climate within a livable range for eons, even as the sun grew brighter. Without this planetary-scale recycling system, carbon would simply accumulate, trapping more and more heat until our oceans began to simmer. Then there is our oversized moon, a celestial companion whose gravitational pull acts as a steadying hand on our planetary spin. It stabilizes the tilt of Earth's axis, preventing wild, chaotic swings that would turn our seasons into a turbulent, unpredictable mess. This lunar anchor grants us the predictable cycles of spring, summer, autumn, and winter, a rhythmic stability that allowed complex life and agriculture to develop. Each of these factors is a marvel in itself, but their true power lies in their confluence. They work together in a symphony of feedback loops and balances. The rotation powers the magnetic field, which protects the water, which lubricates the plate tectonics, which regulates the atmosphere that the magnetic field shelters. It is an interlocking system of checks and balances that has proven resilient to shocks for billions of years. Perhaps the most humbling element in this story is the role of sheer cosmic timing. Earth enjoyed a grace period under a fainter young sun, a stretch of stability that allowed these complex systems to boot up and lock into place before the stellar heat intensified. We were not pushed into a climatic crisis during our planetary infancy, as Venus likely was. Our crises came later, and by then, our planetary immune system was already online, capable of responding and correcting. This sequence of events, this fortunate chronology, may be the most critical luck of all. It means that Earth's habitability is not a default setting for a rocky world. nor is it a permanent guarantee. It is a dynamic, hard won, and ongoing achievement of planetary physics. It is a state of balance maintained by a suite of active processes, each one vulnerable to disruption. Looking back at the scorched fate of our twin, we see not just a warning about greenhouse gases, but a profound lesson in cosmic rarity. The vibrant blue marble we call home is the product of 1,000 delicate alignments, a testament to the fact that in a universe of silent, sterile rocks and blazing infernos, a living world is the most precious and precarious miracle of all. So the ultimate mystery is not just why Venus failed, but why Earth succeeded. The scientific consensus now paints a heartbreakingly clear picture of divergence. Both worlds started with the same raw materials, the same potential for oceans and atmospheres, yet a subtle, devastating cascade of events unfolded on Venus, while Earth navigated a different path. A closer orbit to a brightening sun provided the initial, inescapable push. A slow rotation broke its climate-stirring rhythm and likely doomed its magnetic shield. Without that shield, its water was stolen molecule by molecule. A stagnant crust then sealed its fate, trapping greenhouse gases with no long-term release valve. Each misfortune amplified the next in a feedback loop with no off switch, culminating in a global volcanic reset that erased its past. Earth, by contrast, enjoyed a more distant orbit, a faster spin that powered a protective magnetic field, and the geological gift of plate tectonics, a self-regulating thermostat that has maintained balance for eons. This comparison teaches us a humbling, universal truth. Planetary habitability is not a default setting. It is not a simple matter of being in the right place. It is a dynamic, fragile state of grace, dependent on a complex and precarious interplay of astronomy, geology, and chemistry. A world must possess not just the right ingredients, but the right sequence of events to assemble them into a stable, enduring system. The upcoming missions DAVINCI, VERITAS, and EnVision will transform our understanding from a compelling story into verified fact. They will read the chemical scars in the atmosphere and the mineral fingerprints on the rock, filling in the final chapters of this planetary tragedy. Yet their greatest gift may be perspective. By solving the mystery of our twin, we come to see our own world not as a cosmic given, but as a rare and fleeting achievement. Against the backdrop of a silent, scorching Venus, the vibrant blue of our own pale dot becomes more than just home. It becomes a whispered promise, a testament to the delicate and improbable alignments that allow a world to live, and a reminder to cherish the fragile systems that keep it alive.